Welcome to MRU E-Learning powered by Malla Reddy University. I am K. Uma Kirti, Assistant Professor, Department of IT, School of Engineering. So, today we are going to discuss about the topic NFA to DFA conversion. Before starting this session, I would like to explain you why finite automata transformation is needed. So, what is finite automata? Finite automata is an abstract machine that recognizes patterns from the strings. It is a state machine which has finite memory. It will take the strings and says whether the strings are accepted or not. Where these strings will be coming, it will be coming from regular language. This state machine is a pattern recognizer. It will recognizes the pattern and it will take the language and says whether the language is acceptable with the finite automata or not. The key features of the finite automata are it will take the states and through the input symbols it will say whether the string or the language is acceptable by the machine or not. What are regular languages? The regular languages are the set of strings that can be recognized by the finite automata. For example, if we take a string with ends 0, 1. So, here the strings that end with 0, 1 are 101, 001 and 1101. Meaning these strings ends with 0, 1. So, when the finite automata absorbs these strings, that finite automata gives the output as accepted. If the strings does not end with 0, 1, then it says the finite automata does not accept. Likewise, if we take email formats, there we need to have one @ symbol and it has to have one dot and we need to have few set of strings in front of @. After that, we need to have a domain name and after a dot product, we need to have a com, in or org, etc. If the string follows this pattern, then the finite automata accepts, otherwise it rejects. If the string has only user @, it rejects. If the string has @, domain name, dot and com, then also it will reject the string. So, finite automata has two types. Because finite automata does not have memory in it and it will be in the state, it has two types. One is DFA and another one is NFA. DFA means Deterministic Finite Automata. What is Deterministic Finite Automata? Deterministic Finite Automata is where a state, if we have a state in the finite automata, it will take the input and it will go to exactly one state. Every state must contain one transition for each input symbol. For example, this is the state. A is a state. State is denoted with a circle and this one is an input symbol. The arrow symbols are the transitions. A on 1 it is going to B. A on 0 it is going to A. So in DFA, every state must contain one transition with only one input. So, the destination for DFA is very clear without any confusion. It has to go to one state to another state via one symbol. Just like your GPS. GPS, if we give the destination to it, it will take it and it will go to one destination with the directions it has got. So, the properties of the DFA are, it is easy to implement in code, but the difficulty here is it might contain more states. So, finite automata can be noted with transition diagram, transition table or 5-tuple notation. the phi tuple notation for DFA is defined as M equal to Q sigma delta Q naught F. So what is Q? Q is a finite set of states. The states could be Q naught, Q1, Q2, etc. Sigma. Though we call it sigma, in finite automata, this sigma is called as alphabet. This alphabet consists of few input symbols such as sigma equal to 0, 1 or A, B, etc. Then delta. Delta is a transition function. Here for DFA, the transition function is we take a state with a input and it goes to another state. Next, Q naught. Q naught is the initial state from where the string is started. And F is a set of final states. What are final states? Final states are the accepted states where the string is accepted. Next type is NFA. NFA is a kind of finite automata where the states could accept 0 or 1 or more or nothing is taken. This is acceptable only in NFA. NFA could have 0 transitions or 1 transition or multiple transitions. So here NFA will be having multiple parts. From one state, it could go to any number of states. The properties here are, it is easier to design fewer states, but the difficulty here is backtracking will be done. Why? Because one state could go to so many multiple states. If at all the string is not accepted, then it will come back and again it will go in another path. Again, for NFA, the phi tuple notation is same as DFA, but only the change will come in transition function. Transition function here is from a state, if we take one input, it could go to multiple states. That is why we denote it with 2 power q. This 2 power q means set of states. It could go to set of states. For example, q naught on 0, it could go to q1, it could go to q2, it could go to q3 also simultaneously. So here some ambiguity will be there. But why we have NFA and DFA are, NFA is easier to design, but DFA is easier to implement in code. So for we humans, NFA is more feasible, but for the computer, DFA is more easier and understandable. So how we are going to convert NFA to DFA? Why we need to convert NFA to DFA? Whether we get any problem, first the computer or the abstract machine, finite automata, will take it as a regular expressions. Like your email validations, password setting and all, it will take it as a regular expression. Regular expression then will convert it into regular language. Via regular language, humans, we will construct NFA. Because NFA is easier for us to design, it is okay till here. But for computer to understand, we need to design DFA. So that is why we need the conversion between NFA to DFA. So the algorithm for the conversion is, first we'll be getting a NFA graph. NFA graph will be given to us mostly, or otherwise phi tuple notation will be given for the NFA. From that, we will draw a transition table using that transition function or transition graph. After constructing transition table, then we take a blank table and we start going with the initial state. After initial state transitions are done, from the newly appeared states, we will take them as new states for the DFA, and then we start converting the table into DFA slowly until no new states are formed. After all the states are performed, then we will mark the final states. Here, the initial state of NFA will be the initial state of the DFA. Final states of the NFA are the final states of the DFA. At last, we will be drawing a graph, DFA graph, using DFA transition table. After that, we can give a phi tuple notation for the DFA graph. Let us take an example for this conversion. We have a problem called NFA that accepts strings ending with 0, 1. So, mostly NFA graph will be given to us, or the phi tuple notation will be given, as I said. So, here we got NFA graph which is already given. What this means is we have a Q0 as a starting state. Starting state in NFA or DFA is denoted with arrow mark pointing to a state. This is the initial state in NFA or a DFA. Then double circle means it is a final state. So here our question is, it has to accept the strings ending with 0, 1. So the language here could be 0, 1, 1, 0, 1, 1, 1, 0, 1 or 0, 0, 1 and so on. So here the language is ending with 0, 1. So the machine has to accept the strings whoever it comes with the 0, 1. If the strings are not coming with the 0, 1 as its ending string, then it has to reject. So next, as we got NFA diagram here, let us convert this NFA diagram to transition table. Here what are the states we have? We have Q0, Q1 and Q2. Let us write them here. Q0, Q1, Q2. Next, on Q0, taking 0 as input, where it is going? Q0, taking input 0, it is going to Q0 only. So we will write Q0. Q0 on 1, it is going to where? It is going to two states. One is Q0, Q1. You could see here Q0 is going to Q1 itself and Q0 is also going to Q1. So we wrote like this as a set. Next, Q1, it is going to Q2 on 0. So we'll write Q2. And then Q1 is not going to anywhere with the input 1. So no. Q2 also is not going to anywhere with any of the symbols. So we'll keep blank. After forming the NFA transition table, we need to convert this NFA transition table to DFA transition table. So for NFA transition table, the initial state is Q0. So that will be the initial state of Q0, DFA also. So in DFA, Q0 on 0 it is going to Q0. Q0 on 1 it is going to the set of Q0, Q1. So the newly formed state here is Q0, Q1. So this Q0, Q1 will become the new state of DFA. Q0, Q1. So Q0, Q1 on 0, it forms Q0, Q2. So we'll write Q0, Q2. Q0, Q1 on 1. Q0, Q1 on 1, what it is forming? Q0, Q1 on 1. It is forming Q0, Q1. So now we need to see any new states are formed or not. So Q0 we did already. Q0, Q1 it is done. So next newly formed state is Q0, Q2. So Q0, comma Q2. So next, Q0, Q2. Q0, Q2 on 0, what it is becoming? Q0. Q0, Q2 on 1, Q0, comma Q1. If there is a null state, we don't need to write. We don't need to include in the set. So this is our converted DFA table. Next step. So this is the formed DFA table from the NFA table. We need to draw a DFA graph here. So what are the states here? Q0, Q0, comma Q1, Q0, comma Q2 are the states. So what are the input symbols here? 0 and 1. So Q0 on 0, taking 0, where it is going? It is going to Q0 itself. Next, Q0 on 1, where it is going? It is going to 0, comma Q0, comma Q1. So 1. Next, Q0, comma Q1 on 0, where it is going to? Q0, comma Q1. On 0, it is going to Q0, comma Q2. Next, Q0, comma Q1 on 1, where it is going? It is going to self loop 1. Next, Q0, comma Q2 on 0, where it is going? It is going to Q0. Q0, comma Q2, where it is going? On 1, it is going to Q0, comma Q1. So this is the final DFA graph after converting from NFA graph to DFA graph. If you observe here, we got every input symbol from each transition state. So this is our formed DFA graph. With this, we can form the tuple. What is the tuple for DFA? It is Q sigma delta Q0 F. So what is Q? Set of finite states. What are the states here? Q0, Q0, comma Q1, Q0, comma Q2. These are the formed states for the new DFA. Next, sigma, which is also called as alphabet. Alphabet meaning finite set of input symbols. What are the input symbols here? 0 and 1. So our input symbols are 0 and 1. Next, transition function. Transition function we need to write for each state with each input symbol. Transition function of Q0 on 0. Q0 on 0, where it is going? It is going to Q0. Q0 on 1, where it is going? It is going to Q0, comma Q1. Next state, Q0, comma Q1 on 0. On 0, it is going to Q0, comma Q2. Q0, comma Q1 on 1. Where it is going? It is getting self-looped. Next, Q0, comma Q2 on 0. Where it is going? It is going to Q0. Q0, comma Q2 on 1. It is going to Q0, comma Q1. This is how you form a graph, transition table and phi tuple notation. So at last, I want to conclude the session by saying whether we are using the text editors, compilers, security information or intrusion detection, bioinformatics, everywhere we are using these finite automata. This we are not only studying for exam purpose, we are doing this for how we are using the software under the hood. Thank you.